Alright, so today we're going to be doing 7.5, which is going to be graphing rational functions. So in this lesson, we're not going to be covering any new material per se, but we're going to be bringing everything together. So we're going to be talking about how all of these different lessons kind of interact with each other and how they all kind of come back into one concept. So we've talked about each of these types of functions throughout this lesson or this unit. We talked about reciprocal functions, transformations, and rational functions. So this sheet right here is going to be putting everything together into one little organized, divider situation. So basically, if you're on a quiz or something like that, it's going to be really helpful because this sheet will kind of give you all the key features of all these types all on one page. So let's talk about parent function, the reciprocal function. So this is like 7.1 when we learned 7.1. So does anybody remember what the reciprocal function parent function is? It's y equals 1 over, anybody remember what's in the denominator? X, very good. So this is what we call our reciprocal parent function. So that's the first thing we learned about in Unit 7. And the reciprocal parent function looks like this in its general form. It has its two branches. So we've been talking about functions that have this type of appearance. And this is basically the parent of all of that. And then we'll talk about what their asymptotes are. So in this one, we can actually look at the asymptotes on the graph itself first. So what I like to do is actually find them looking at the graph. So I can see here that I have a horizontal asymptote here, and I have a vertical asymptote right here. So the equation for my vertical asymptote is x equals 0. And what would be the equation of my horizontal asymptote? Good, y equals 0. So that's just based on my graph. That's based on properties of the reciprocal parent function.
Why did you put 0 again?
Just because, see how these two lines on the graph are two lines that you can draw that will hit neither branch? That's why. So technically speaking, horizontal asymptotes can sometimes be crossed, but they will kind of show us where the graph's bending, what its end behavior looks like. And vertical asymptotes will never be crossed, ever. So you can always use that as a guide to where your graph will never cross, defining what an asymptote is. And then lastly, we'll talk about the domain and range of this. So this function is defined on every x value except for which x value can it not touch? 0. So from negative infinity to 0, union 0 to positive infinity. And this graph is defined on every range value except for 0. As you can see, it doesn't touch this value right here. So from negative infinity to 0, union 0 to positive infinity. So that's its domain and range. And the domain and range for reciprocal functions will always be this setup, where this value right here in the domain will be your h, and this value right here in the range will be your k. And that's for all of the reciprocal functions in this format. So if that helps you remember, that's how it's always set up. So any questions about the reciprocal functions? So these are like the most generic form, basic form of these functions. And then from here, we learned about transformations of these functions. So that was the next thing we learned about, 7.2, 7.3. I believe it was 7.2. And the standard form for that is y equals a over x minus h plus k. So we took this function and we applied transformations to it. And we're going to talk about the several different types of transformations that were applied to this function. So does anybody remember what kind of shift the h represents?
Horizontal.
Good, horizontal. And does anybody remember something unique about the h in particular that the other letters don't have? Yeah, it's negative, so it changes sign, right? So if in the formula it is positive, it's actually going to the left. And if in the formula it's negative, it's actually going to the right. So keep in mind that h always changes sign when placed into the formula. because of the nature of the formula itself with the negative sign. And then if h is horizontal, what do you think k is? Good. The k represents a vertical shift. And vertical shifts are up and down. So k is as is, so if it's negative, it's going down. If it's positive in the formula, it's going up. It does not change sign in the formula. And now we're going to talk about the effects of A. A can have 3 different effects. If your A value is greater than 1, it represents a vertical stretch. Good. And if your A value is between 0 and 1, it represents a vertical, good, compression. And yes, of course, the A value taking the absolute value of, because we don't care about negatives with stretch and compression. And if your A value is less than 0, aka negative, good, it represents an x-axis reflection, meaning it's reflected over the x-axis. And then from here we can define the vertical and horizontal asymptote. So your vertical asymptote when in this form is always x equals h. And remember your h changes sign here. So if it were negative in the formula, it's going to be positive here and vice versa. And your horizontal asymptote is y equals k. Does everybody remember that? Vaguely? Okay. So that's transformations. That was 7.2. So then 7.2 and 7.3. Then we moved on to 7.4. So 7.4, we talked about rational functions in what we call general form. So general form looks like this. Y equals P of x over Q of x. And what that means is we basically just have 2 separate expressions as entities as a fraction. And another way that this can be represented also, which you'll see, and I'll write this out for you, is A times x to the m plus dot 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 over b times x to the n plus dot dot dot. So what these represent right here, a and b, these are coefficients of leading term. So those are the coefficients of the leading term. So if you want to write that in, you can. Basically, that just represents what the coefficient is, and we sometimes use that in these processes to find different things, like the horizontal asymptote. All right. So now we're going to talk about the 3 different types of horizontal asymptotes that can occur when we're in general form. So does anybody remember what happens when you have a top-heavy degree? The degree on the top is bigger than the degree on the bottom. It means we have no horizontal asymptote. And this is all from 7.4 notes. And does anybody remember what the equation of the horizontal asymptote is when you have a bottom heavy degree? Y equals 0. And then the last one is when we have the same degree, and this is where A and B come into play. Does anybody remember this one? This one's the one we use the most. Y equals
1.
Good, A over B, which often does come out to be 1 if your coefficients are 1 and 1. So these are the 3 different types of situations dealing with horizontal asymptotes based on your general form of your rational function. Now moving on, we're going to talk about discontinuity. We learned about 2 different forms of discontinuity, removable and good. So we have removable type. I meant to put an R there. I failed. These are the type that can be removable, and these are the types that are non-removable.
Excluded? Is the one removable excluded factors?
Cancel factors appear as, yes, you're right, excluded, but we use another word for it. It's called like a hole. But yeah, you're right.
Okay.
You just use a different term. Holes in the graph, aka yes, excluded. So anything that any factors that cancel out appear to be holes in the graph, like they literally have like an open circle. Okay. And then non-canceled factors in the denominator represent, what do we call these? Vertical. Good. Vertical asymptotes. So those represent vertical asymptotes. So those are the removable and non-removable types of discontinuity in our graphs. Now next we're going to talk about our x-intercepts. So when we're in this form, x-intercepts occur where non-canceled factors of the numerator equal 0. So the way that we find x-intercepts is we set any of the products in our numerator equal to 0 and solve for them, okay? And we find y-intercepts by replacing all the x's with what and simplifying? 0, good. We replace all the x's with 0 and simplify, which is how you find y-intercepts for any type of function anyway, so that's not too unique. So from here, we'll go ahead and do our example, and then we will have time for work. And if anybody has questions about old lessons, we can use that time too. All right. Moving on. So it says use long division to rewrite, or you can use long division to rewrite some rational functions in general form, from general form into standard form. So what we're going to be talking about today is we've been looking at these three things as three separate entities, but they're actually of the same parent function. So all three types of functions we've been looking at really are all just manipulations of that parent function. And they're in just two different forms, general form and standard form. So we're going to learn how sometimes we can actually convert them from one to the other. So we use long division. I usually prefer to use synthetic division when possible. So I will be using synthetic division on this one. Just keep that in mind. I think synthetic division is easier to remember and easier to do. So typically, if I can, I will use synthetic division. So this one right here, is this in general form or standard form, this one? Good. This one is in general form, right? I can tell it's in general form because I can't identify a k value. The a value is not a number. It's clearly not in standard form. So we want to go from general form to standard form. So to do that, I'm going to zoom in here. And I'm going to use my properties of synthetic division. We don't have a ton of room. I apologize for that. So go ahead and draw yourself a little synthetic division bar, like you would. Make mine a little better. Hang on. Go a little higher on it so we have more room. It's going to be a little tiny one, so don't worry. It doesn't need much room. And remembering back to when we did synthetic division, does anybody remember what goes on the outside? If we have x, we're dividing by x minus 1, it's going to be what out here? Good, a regular positive 1. And then we're going to take the coefficients of my numerator. So that's going to be 2 and 4. And this one only has 2 terms, and we have no placeholders. The last part of the synthetic division will be the remainder, so you can put a little line there to indicate it. And then we're just going to proceed with our synthetic division as we normally would. We bring down our 2, we multiply 1 times 2, and we combine. So that's what we end up with as a result of our synthetic division. So right here, what does this 2 represent? It represents not the coefficient of x, that would be if we had another one, but this one's actually the constant, just the 2, right? So if we had another value over here, that would have been the coefficient of the x. So it goes constant, coefficient of x squared, and so on, whatever we have left. But this is one where we only have 1 left, which isn't typical. You don't see that very often. So this is just 2 plus, and then the way you write your remainder is, it's going to be remainder over the divisor. What was our original divisor?
X minus 1.
Good, x minus 1. So this right here would be the equation after synthetic division. Now, in this case, it's starting to look pretty similar to standard form, but how can I make it look even more similar to standard form?
Flip y.
Not flip the y, you're on the right track. It's going to be, yeah, you're right. Yeah, flip the y and also flip these 2 terms, right? So see how when I flip those around, it looks a lot more like standard form now? So we basically just converted it to standard form. So as we go through this process of identifying the key features of this graph, I will be talking about them in terms of standard form and general form to remind you how they work and how you could identify either way. So I'll be using both, And I will do the general form ones in red, and I will do the standard form ones in orange so you can keep track. So, the way we find the horizontal asymptote when we're dealing with general form is we first have to identify if it's top heavy, bottom heavy, or the degree is the same. What is the degree of this numerator right here?
1.
Good. And what's the degree of the denominator?
1.
So the degrees are the same, which means the horizontal asymptote is
1.
well, no. A over B.
I thought it was the H value.
What?
I thought, wasn't it the H value? Like, oh, no, never mind. Wrong one.
So when the values, the degrees are the same, it's A over B, which are the coefficients of the leading term. So what's the coefficient of the x up here?
2.
Good. And what's the coefficient of the x in the denominator? Good. So our horizontal asymptote comes out to be 2. And that's how we would do it using general form. Now, if we're talking about standard form, the way we identify the horizontal asymptote is just y equals what value? It's right on the front of the top of the notes under horizontal asymptote. Y equals
Okay.
k. So what's the k looking at my standard form here? 2. So see how we were able to identify it both using both methods and it comes out to be the same? Because reality is these two functions are the same thing represented in two different ways. So yes, the horizontal asymptote would be consistent. Now as for the factoring portion, this one doesn't have any factoring to complete, but the one in the red has some factoring that we can do. So what can we factor out of the numerator of the general form? We can factor out a 2, right? So if I factor out a 2, that's just going to leave me with x plus 2, 2 times x plus 2, all over x minus 1. So that's its factored form. So for a little bit here, we're going to talk in terms of the red equation, the general form. We're going to talk about removable discontinuity. This only occurs if this equation, something cancels out in it. So in this equation, can anything be canceled out here? No, because we don't have any like factors in the numerator or denominator, meaning that we have none of these, so no holes. And that's because nothing cancels. Now, if we did have anything that canceled, you would set whatever canceled out equal to 0 to find the x coordinate, plug it back in to find the y. But there wasn't any situation of that occurring here. So now we're going to talk about non-removable. So a non-removable discontinuity is also known as a vertical asymptote. Okay, that's another terminology for it. And the way we find this is we take whatever our denominator is and we set it equal to 0. So do we have a denominator here? In this? Good. We take x minus 1, we set it equal to 0. And then we just solve for x, which comes out to be x equals 1, being my vertical asymptote. So that's how we would do it using general form method. Now, if we're talking about standard form method, we know that our vertical asymptote is defined by, according to your notes, x equals, it's right above this, h. But remember, your h has to change sign. So if we look back to our standard form, which number here represents my h? The -1, but it has to switch signs, which gives me x equals 1. So see how you get the same answer either method. Okay? So that's my non-removable vertical asymptote. Now we will move on to intercepts. So to find intercepts using general form, I prefer to use general form if possible. I'll just recap quickly on how to do it with standard in case you want to know. To find an x-intercept with standard form, you just replace the y with 0 and solve for x. To find the y-intercept, you would just replace x with 0 and solve for y. So you basically just plug in 0 for the opposite one that you're looking for and solve for that variable. Now, if we're using general form, there's actually a little bit of a shortcut using general form. General form states that we only need to take the numerator for the x-intercept and set the numerator equal to 0. So when we do that, that's going to come out to be x equals -2. but we want to write that as an ordered pair. I don't know why I'm circling it yet. We're not quite done yet. So that's going to come out to be negative 2, 0 as my x-intercept. Take the numerator, set it equal to 0, solve for x. That's my x-intercept.
Wait, so we take the numerator of just the entire thing and just set it to 0?
Correct. Factored or pre-factored will give you the same answer. Alright, so now we're going to move into y-intercepts. So to find the y-intercept using general form, you just take the original equation, or the factored form, it doesn't actually matter, and you just replace all of the x's with 0 and solve for y. So I'm just taking my original equation, replacing all of the x's with 0. I just made a mistake here. Hang on. There we go. I put a plus instead of a minus. And then you're just going to complete the math there, and I think I wrote it out. When I did, I think it's negative 4. Yeah. It comes out to be 0, negative 4. So to find the domain and range using general form, you actually have to graph it first. Do you remember that? However, standard form actually has a really easy method in finding the domain and range that we talked about earlier. Domain is always negative infinity to h, which my h is 1, union h to positive infinity. So that's just a formula. These values right here are h. And if that one's h, then what do you think the range is? Good. Okay. So all that means is we're basically including every value for x except for h and k, because those are your vertical and horizontal asymptotes. So from here, we want to wait to do end behavior after we graph. So now we're going to go ahead and graph. Before you start using Desmos, the first thing I want you to do is graph the asymptotes you just found. So it looks like we found 2 asymptotes. We found a vertical and a horizontal one. So it looks like we have a vertical asymptote at x equals 1, and we have a horizontal asymptote at y equals 2. And once you've graphed your asymptotes, you're going to move into graphing your intercepts that we found. So we found that we have an x-intercept at negative 2, 0. And we found that we have a y-intercept at 0, 4. Negative 4, my bad. So that's what we know so far about our graph using what we have come up with. Now, this is where Desmos comes into play, because you could try to guess and check some points. However, we want to make our lives easier, and we want to use software when possible. So I'm pulling up Desmos here to talk you through the process from the beginning in case you haven't seen it. So you have Desmos up. You're on a phone, you're on a computer, whatever you're using. There is an app on your phone for this. It's free. And the first thing you're going to do is you're going to type in your equation. Now, it doesn't matter if you use general or standard form. Why doesn't it matter? Is the graph going to look different? No.
It's the same equation.
Exactly. It's the same equation. So either form will work, and you can test this out yourself if you don't believe me. Plot both. They'll overlap each other. This is the equation. And then we are going to graph our asymptotes. So we have one at x equals 1, and we also have one at y equals negative 2. No, positive 2. Like that. So as you can see, it bends around the asymptote, and we have our graph here. We have a general look of what it looks like, which does match what we have so far, right? Now, to get more precise, there's this little gear button on Desmos that you can click on, and it will give you an option to convert your values to a table. Okay, so you click on this little button, convert to a table, and this will allow you to find any input and output value you choose. So I want to try to figure out what's going to fit on my graph, what's going to help me figure out what's next. I have 2 points here, but I want to figure out a point in the middle, so I'm going to try to plug in negative 1 and see what it tells me. Well, when I type in negative 1, it gives me negative 1 as my output. So with that information...
Ms. Russ, I have a question real quick. How
Sure.
did you get that table again on
you go to the little gear button and then click, if you click this, it will give you an option to click table. I can't it won't let me go back right now, but I can show you at the end if you want. So then from here we found out that it's at -1, -1. And now that I have approximately 3 to 4 points, I can graph this, get a general look of what the graph looks like. So that's half of my graph. Now we also have another branch of the graph over here according to my graph. So I want to find some points over here I can plug in. So I'm going to try plugging in a 1. I'm sorry, not a 1, that wouldn't work. That's the asymptote. What if I try a 2? Well, it tells me at 2, 8 there's a point. So at 2, 8, 1, 2, and then 6, 7, 8. So at 2, 8. So that gives me some idea. And then maybe if I plug in a 3, so if I go to my table, I can type in 3, and it will give me the output, which is 5. So at 3, 5. And then I'll try plugging in a 5. And at 5, there's a point at 3.5. So 1, 2, 3 and a half right here. Now that I have about 3 points, I can finish my graph. It'll look something like this. Now that we've identified that, we can now identify its end behavior. So, on both sides, on the left, my graph's getting closer and closer to what value? Not quite, because it's bound by this positive 2, yes. So it's bound by my asymptote at positive 2. And over here, once again, it's getting closer and closer to my asymptote over here as well, which is at 2. So the horizontal asymptotes typically help us identify end behavior.